Good morning, students. Hope you all are fine and safe at home. So, today we will discuss about our next topic of chapter 1, that is the Dalton's atomic theory. So, John Dalton proposed a theory which was known as the Dalton's atomic theory. With this theory, many concepts regarding matter, composition of matter, atoms, and even combination of atoms resulting compounds were better understood. So let's take a very quick look at 6 major postulates of this theory. First, he said that all matter is made up of very tiny particles called atoms. So we will write that all matter is made up of very tiny particles called atoms. Okay, so this is our first postulate of Dalton's atomic theory. Second, he suggested that atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. In a chemical reaction. And the third one is atoms of a given element are identical in mass and chemical properties. Similarly, fourth postulate was that atoms of different elements have different masses and chemical properties. Atoms of different elements have different masses and chemical properties. So this was our fourth postulate. Fifth postulate stated that atoms combine in a ratio of small whole numbers to form compounds. We will write atoms combine in a ratio of small whole numbers to form compounds. And lastly, we have the relative number and kinds of atoms are constant in a given compound. So these are our six postulates of Dalton atomic theory. So we will now explain, or we will understand these postulates in detail one by one. So let us now understand each postulate one by one, taking same example of elements A and B giving rise to C. We will write that we have element A and element B which is forming a compound C. So, according to the first postulate, the first point stated that all matter is made up of very tiny particles called atoms. So it means that when we go on dividing atom into smaller and smaller sections, we get at the end is atoms. So can we say that elements A and B are made up of atoms? Yes. We have element A, for example, this is our element A and this is our element B. So both these elements A and B, they are actually atoms and they are forming compound C by joining elements A and B, or the atoms of elements A and B. So in fact, the compound C is also made up of the atoms that have combined together. So the first postulate was very easy to understand. And now, the second one we have. The second postulate was that atoms are indivisible particles which cannot be destroyed in a chemical reaction. Now, what do we mean by this? Yes, it means that atoms are like the fundamental units. Dividing them further is not possible. Also, in a chemical reaction, atoms may combine together to form new units. We know that in a chemical reaction, atoms may combine together to form new units, like element A is joining with element B and is forming a new unit of compound C. However, no new atoms can be created and existing ones cannot be destroyed. So, we have two atoms and they are forming a unit compound C. This is A and B, this is C. And both these are atoms and they are forming a fundamental unit. So, in this case, atoms of A and B are just combining to form compound C. Okay, understood? So, can we say that no new atoms are formed in this case? Yes. Similarly, no atom is destroyed in this case. Let us move on to the third one now. The third postulate stated that the atoms of a given element are identical in mass and chemical properties. Let us understand this. If we zoom into element A, for example, we have element A. We have element A, and if we zoom into element A, we find that all the atoms that make up element A are just the same. You can understand this by drawing these lines in the element A, and you can draw the atoms in the element A. And we will find that atoms that make up the element A are just the same. That means all these atoms in the element A are same. And in what sense are they same? The atoms have the identical mass as well as same chemical properties. In simple words, the third postulate states that atoms of a given element are identical in mass and chemical properties. And does this explains the fourth postulate too? Yes. The fourth postulate states that atoms of different elements have different masses and chemical properties. So, what we will take? We will take two elements, that is A, where we have these types of atoms that we already draw in the previous postulate, and a second different element with different types of atoms. To show the difference, I drew the different lines. So, are we able to notice that atoms in element A are different from those in element B? Absolutely. And in what sense are they different? That atoms in element A and element A and B have different masses and different chemical properties. That means they both have different mass and different chemical properties. So, in simple words, it states that the atoms in different elements are different. Now, the fifth one. The fifth postulate states that atoms combine in a ratio of small whole numbers to form compounds. Now, what do we mean by this? In this chemical reaction, we have a chemical reaction that element A we have and element B we have is forming a compound C. In this chemical reaction, we find that elements A and B are reacting to form compound C. If we observe carefully, then we will see that in compound C, there are two atoms of element A and one atom of element B. Right? So, are these whole numbers? Yes. This means in any compound, the elements are always present in a ratio which comprises of whole numbers. This means in any compound, the elements are always present in a ratio which comprises of whole numbers. For example, in case of water, we always have, we will take the example of water. The formula of water is H2O, where we have two atoms of hydrogen and one atom of oxygen in 1 unit of water. We have in carbon dioxide, that means we have a compound unit carbon dioxide where we have one atom of carbon and two atoms of oxygen. So, the same is true for all compounds. The number of a particular element in a compound will always be a whole number. Understood? So, now for the last one. The sixth postulate states that the relative number and kinds of atoms are constant in a given compound. So, what it means that the relative number and kinds of atoms are constant in a given compound. The same explanation that the compound C has two atoms of element A and one atom of element B makes us understood this. We took the example of element A and B, which is forming compound C, where we have two atoms of element A and one atom of element B. The same example we will take in the sixth postulate. What does it mean? If we scan compound C, for example, we are zooming to compound C or we are scanning to compound C, which will show that the two atoms of element A, we have two atoms of element A and one atom of element B in a single unit, and this is applicable for all the compounds. We have already looked into the example of water and carbon dioxide. For example, this is the unit compound of carbon dioxide, where we have two atoms of oxygen and one atom of carbon. In case of 1 unit of water, we already took the example of the water here, so we will not take it again. And you can take another example like that in case of the ammonia, where we have one atom of nitrogen and three atoms of hydrogen. That means one nitrogen atom bound to 3 hydrogen atoms. So the number of atoms will always be constant in a unit of particular compound. Okay, understood? In a nutshell, these postulates help chemists to further understand the behaviors of elements and the compounds formed from them. But for understanding these elements and compounds, knowing the concept of atoms and molecules is necessary. Okay, so we will discuss now that what is an atom. Atom is the ultimate particle of an element. To understand this, consider a piece of element. Say we are taking a piece of gold or any piece of brick or any piece of, or you can take any stone. If we break this into smaller and smaller pieces, it will become so small that we will not be able to see it without a microscope. If we keep on breaking this particle, we will ultimately reach a stage when this particle cannot be further broken. This ultimate particle of an element is called an atom. Thus, the smallest particle, you will now write the definition of atom. The smallest particle of an element which may or may not have independent existence is called an atom. Okay, the smallest particle of an element which may or may not have independent existence is called an atom. The atoms of certain elements such as the hydrogen, like oxygen, nitrogen, etc. are not capable of independent existence. Not independent existence. And whereas atoms of helium, neon and argon etc. are capable of independent existence. All elements are composed of atoms. You know that all the elements are composed of atoms. There are about 114 elements known, and obviously there are 114 different types of atoms. Okay, so now what we have next, a molecule. Just as the ultimate particle of an element is atom, the ultimate particle of a chemical compound is called a molecule. This is not the exact definition. I am just telling you or making you understand that the ultimate particle of an element is an atom, but the ultimate particle of a chemical compound is called a molecule. So, when two or more atoms of different elements combine, the molecule of a compound is formed. For example, H plus H. These are the atoms of hydrogen, and they are forming a molecule of hydrogen, that is the H2. This means that hydrogen cannot be in the independent existence. These need to be added with another atom or another element. So, next you can take the example of the oxygen. Similarly, oxygen is adding with atom of another oxygen, so it will make a compound or a molecule of oxygen with the formula O2. The molecules are made up of the atoms of the same or different elements and are capable of the independent existence. That means the molecules are made up of the atoms of the same or different element. That means the molecules will made with the same or with the different elements. That when they will attach with, or when they will add with the same elements or the different elements, they will be make the independent existence. Thus, now we will define that the smallest particle will define molecule. The smallest particle of a substance could be any element or compound which is capable of independent existence is called a molecule. The smallest particle of a substance which is capable of independent existence is called a molecule. Thus, a molecule contains two or more atoms. The properties of a substance are due to the properties of its molecule. Understood? So, after having some idea about the atoms and molecules, it is appropriate here to understand what we mean by atomic and molecular masses. So we are moving to the next topic, that is atomic and molecular masses. So atomic mass, we will first do atomic mass. An atom of an element is so small particle that its mass cannot be determined even with the help of the most sensitive pens. For example, by an indirect method, the absolute mass of hydrogen atom has been found to be, that means the mass of hydrogen, 1.6736 multiplied 10 raised to power minus 24 gram. With an it is by indirect method the absolute mass of the hydrogen atom. Such extremely small numbers are very inconvenient for calculation. That means this is very small number which is inconvenient for the calculation. The difficulty was overcome by expressing atomic masses as relative masses. That means with respect to the mass of an atom of a standard substance. Earlier, the chemist selected hydrogen atom as the standard substance because it is the lightest of all known atoms. The atomic mass of hydrogen was taken as 1. Atomic mass, you know that atomic mass of hydrogen is 1 and it was taken 1. Thus, the atomic mass of an element is the number of times of an atom of that element is heavier than an atom of hydrogen. I am repeating, the atomic mass of an element is the number of times an atom of that element is heavier than an atom of hydrogen. But you will write the definition of atomic mass is that atomic mass of an element is heavier than the atomic mass of an element is the number of times an atom of that element is heavier than an atom of hydrogen. The relative atomic masses were referred to as the atomic weights. We know that mass is equal to weight, so the relative atomic masses were referred to as the atomic weights. For example, it has been found that an atom of oxygen is 16 times heavier than an atom of hydrogen. That means oxygen is 16 times heavier than an atom of hydrogen. Thus, the atomic mass of oxygen relative to hydrogen is 16. That means atomic mass of oxygen is 16. Later on, oxygen was fixed as the standard because it is more reactive than hydrogen and forms a large number of compounds. But in 1961, the International Union of Chemists selected a new unit for expressing the atomic masses. They accepted the stable isotope of carbon with mass number 12 as the standard for comparing the atomic and molecular masses of elements and compounds. Nowadays, this scale depends upon the measurement of atomic mass by an instrument known as the mass spectrometer. The name of the instrument to measuring atomic masses of different elements. The atomic mass can be determined on this instrument by comparing the mass of an atom with the mass of particular atom chosen as standard. That means we will take a standard unit of mass. That means we are taking carbon 12 as a standard unit of mass. We will compare the atomic mass of which we have to find. This scale of relative mass of atoms is called the atomic mass unit and is abbreviated as AMU. That means when we are finding the atomic mass, we will write that means atomic mass of oxygen is 16 AMU. But however, the new symbol used is U. It is changed into U and is known as the unified mass, which has taken the place of the AMU. Hence, one atomic mass unit. The one atomic mass unit is defined as the quantity of mass equal to quantity of mass equal to 1 upon 12th of the mass of an atom of carbon. We will write carbon 12 like this. So this is the definition of the one atomic mass unit, or 1 AMU. It's the quantity of mass equal to 1 upon 12th of the mass of an atom of carbon 12. The atomic masses of some common elements. For example, you know that the atomic masses of some common elements, like you know about the mass of the atomic mass of the oxygen, atomic mass of the hydrogen is 1, atomic mass of the carbon is 12, atomic mass of some other elements like lithium or like aluminium is 27, the atomic mass of nitrogen is 14, the lithium, I repeat, is 6.94. You can take it approximately 7. Okay, so now we will exactly define what is the atomic mass of an element. The average relative mass of an atom of an element as compared to the mass of an atom of carbon taken as 12. But you will write here the atomic mass of an element is the average relative mass of an atom of an element as compared to the mass of an atom of carbon we will take like this, taken as 12. Understood? In other words, the atomic mass is a number which expresses as to how many times an atom of the element is heavier than 1/12 of the mass of carbon atom. I am repeating that atomic mass is a number which expresses as to how many times an atom of the element is heavier than 1/12 of the mass of carbon atom. Therefore, the calculation for this, or the formula for this atomic mass, is mass of an atom divided by 1/12 mass of a carbon atom. For example, the mass of an atom of hydrogen how you will calculate this? The mass of the atom of hydrogen is 1.673 into 10 to the power minus 24 gram. In terms of AMU, you have to calculate it in terms of AMU. 1 point, that is the 6736 into 10 to the power minus 24 gram. 1.6736 into 10 to the power minus 24 gram is the mass of an atom of the hydrogen element, and you will divide it by 1.66056 multiplied 10 to the power minus 24 gram, and what you will get 1.0078 AMU, or approximately 1.0080 AMU. That means the atomic mass of hydrogen is 1.00 atomic mass of hydrogen 1.008 unit. That means at the place of AMU you will take unified mass. This means that an atom of hydrogen is 1.008 times heavier than 1/12 of the mass of carbon atom. An atom of oxygen is 16 times heavier, and so on. It means if you will calculate the atomic mass of the oxygen atom, you will find that the atomic mass, you will calculate that the atomic mass of the oxygen is 16, and you will say that oxygen is 16 times heavier than 1/12 of the mass of carbon atom. Understood? So we are moving to our next topic, that is the average atomic mass. The word average has been in the above definition and is very significant. It has been found that the majority of the elements occur in nature as mixture of several isotopes. But it says that the majority of the elements occur in nature as mixtures of several isotopes. You already know about the isotopes that you studied in class 9th, that isotopes are the different atoms of the same element possessing different atomic masses but same atomic number. Okay, isotopes are the different atoms of the same element possessing different atomic masses but same atomic number. Or you can simply say that atoms with different atomic masses but same atomic number are known as the isotope. The average relative atomic mass depends upon the isotopic composition of the particular element. The mass spectrum gives information regarding the masses of the isotopes and the relative abundance. I'm repeating that the mass spectrum gives information regarding the masses of the isotopes and their relative abundance. This helps to calculate the relative atomic masses, but helps the relative abundance and the masses of the isotopes. That means to calculate the average atomic mass, you have to know about the relative abundance and the mass of the isotopes. Okay, the fractional abundance of an isotope is the fraction of the total number of atoms that is composed of the particular isotope. The best way to define atomic mass of these elements is to determine the atomic mass of each isotope separately and then combine them in the ratio of their proportions of occurrence. This is the formula which we will use in our example. This is called the average atomic mass, or you can write the definition of the average atomic mass is that the atomic mass of each isotope separately and then combine them in the ratio of their proportions of occurrence. So this is called the average atomic mass. For example, we know that the carbon occurs as the three isotopes. The isotopes of carbon with atomic masses 12, 13 and 14, and the abundance of these isotopes in the percentage. 98.892 is the percentage of the carbon with atomic mass 12 and 1.108% for the carbon with atomic mass 13 and 2 multiply 10 is to power minus 10% for the carbon with atomic mass 14. And the atomic masses for these isotopes. For the carbon with 12 atomic mass is 12, for the 13 is 13.00335 and 14.00317 for the isotope with 14 atomic mass. Therefore, to calculate the average atomic mass of carbon, what you have to do, you have to write first abundance, then multiply it with their atomic mass. The second relative abundance with their atomic mass, or you can simply write the 13, the exact or the round off figure, and the third isotope abundance is this, and multiply it with their atomic masses and divide them with the total composition of the compound. That means we are taking the 100 gram is the total composition of the compound. So to calculate this, when you will calculate this example, you will find that the relative atomic or the average atomic mass for the carbon is 12. Let's move on to the next is the molecular mass. Like atoms, the actual masses of molecules are also very small and cannot be measured by actual weighing. Like atomic masses, molecular masses are expressed relative to the stable isotope of carbon 12 having mass number 12. Thus, the molecular mass of a substance may be defined as the average relative mass of its molecule as compared to the mass of an atom of carbon taken as 12. In other words, molecular mass expresses as to how many times a molecule of the substance is heavier than 1/12th of the mass of an atom of carbon. I am repeating that molecular mass expresses as to how many times a molecule of the substance is heavier than 1/12th of the mass of an atom of carbon. For example, a molecule of carbon dioxide is 44 times heavier than 1/12th of mass of carbon atom. Therefore, the molecular mass of carbon dioxide is 44 AMU. And how you will calculate the molecular mass of carbon dioxide? That means that you got the 44. I am saying in the definition that the molecular mass of the carbon dioxide is 44 times heavier than the 1/12th of the mass of carbon atom. You will calculate this with a simple method, that molecular mass from atomic masses. You will calculate the molecular mass from atomic masses. The molecular mass may be calculated as the sum of the atomic masses of all the atoms in a molecule. That means you have to add all the atomic masses. For example, the molecular mass of methane, that is the formula of the methane is CH4, and the formula for this atomic mass of carbon with the number of molecules we have 1 and plus atomic mass of hydrogen, the number of molecules we have here is 4. Multiply it with 4. This formula you already done, this method you already done in your 9th class. Now we know that the atomic mass of carbon is 12. Multiply it with 1, and the atomic mass of hydrogen is 1. Multiply it with 4. So now 12 multiply 1 is 12 and 4 multiply 1 is 4. That means what you will get is 16 U is the molecular mass for methane or methane gas. And what I was talking in the definition, that the molecular mass of carbon dioxide, you have to first write the atomic mass of carbon that is 12, and the number of molecules or the number of atoms in carbon is 1, and plus sign, the atomic mass of oxygen is 16, and multiply it with the number of atoms. How many number of atoms are present here? That is 2. So 12 plus 12 multiply 1 is 12, and 16 multiply 2 is 32. When you will add these both, you will get the 44. U is the molecular mass for the carbon dioxide. Understood? So last we have the formula mass. What is the formula mass? To understand this, first you have to listen this. Some substances such as sodium chloride, potassium chloride, these both are the ionic compounds, do not have discrete molecules as their constituent units. In such compounds, positive, that means sodium, and negative, that are chloride ions, are arranged in a three-dimensional structure. You know that the formula of the sodium chloride is NaCl, and this is an ionic compound. Ionic compounds means this have two types of ions, positive and negative. The sodium has positive ion and chlorine or chloride has negative ions, and both these ions are arranged in a three-dimensional structure. In this structure, it has been observed that the structure we will make here, that the sodium, we will draw a single round figure, that is, this is the sodium, and in three-dimensional structure means that there are 6 chlorine atoms that are surrounded to the 1, 2 on the front and back side of the sodium. That means in this structure, it has been observed that each sodium ion is octahedrally surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. In these compounds, we call formula unit rather than molecular formula, which gives the simple ratio between various ions present. So, for these compounds, we use formula mass instead of molecular mass. The definition is same, that formula mass is the sum of atomic masses of all atoms in a formula unit of the compound. For example, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chloride. What is the atomic mass of the sodium is 23, and atomic mass of chloride or chlorine is 35.5, and when you will add this, what you will get, 58.5. okay, so we have reached at the end of the topic. So if you have any problem, then you can contact me on my number. Okay, thank you, bye bye.